Hello, my name is Pete, and I'm going to take you through the topic of damping, which is lesson 2 this week. The images on the screen you can see are all examples of mechanical systems where damping is utilized. You might have come across the term before. In fact, all oscillating systems that we come across in the real world will have some form of damping. Sometimes damping is a real problem and you need to overcome it in cases of certain examples like buildings. Sometimes it's more for comfort. Sometimes it can be to enhance something such as in music. But all of these examples have got lots of things in common. So once you've learnt the basics, you can apply it to lots of different examples. So you are going to need a pen and paper, and at stages in the video I'll ask you to pause and then draw something and then come back when we look at the answer together. Okay, so first thing we're going to look at then is what do we mean by damping. So if you get yourself a pen and paper, the first task, what is damping? I'd like you to look up a definition for it. It is going to be much more useful to you if you do pause the video and try and work out some of the answers rather than just pressing ahead, because you won't engage so much. So if you have something to do and then to pause the video, try doing it, and I think you'll get more out of it that way. So look up a definition, and then number 2, sketch a graph of displacement against time for a damped oscillator. What might you expect to see for the displacement against time? Okay, so if you'd like to pause the video now, have a go at that, and then when you're ready, we'll carry on. Okay, so hopefully you've got something along the lines of what we have here. An oscillation is damped when an external force that acts on the oscillator has the effect of reducing the amplitude of its oscillations. We need to tease out some of the terms here. What do we mean by an external force? Because we already know that there is a force involved in oscillations which causes the acceleration. So we need to make sure we're clear about what this external force is. And then if you've got something looking a bit like this graph, your sketch, what's the significance of this blue dashed line here? And the term light damping. We're going to come across all those terms as we go through the rest of the video. So in order to try and show you some more about this, we're going to look at one of the PhET animations called Masses and Springs, and I'm going to look at the section on energy. So I'm going to jump to that applet now. And when I've got that ready, I'll ask you a question. Okay, so here we have our applet, our animation ready. So let's just set this system going. We've got a mass on a spring that's oscillating, and the dashed line here is the equilibrium position. That's where the mass would normally rest. This red line is an arbitrary one that I've put in. I can drag this point to wherever I like, and I am going to start the oscillations by taking the mass, so the bottom of the mass is level with the red line. The system says that there's no damping. We haven't really discussed what that means yet, but we've got 0 damping at the moment. And over on the left-hand side, I'm not going to spend too much time on this today, but there is a breakdown of the energy as the oscillation takes place. So I'm going to press the play button, and we'll just watch what happens for a second. So first of all, we can see that there doesn't appear to be any decrease in the amplitude over time. It keeps returning back to the original position. The energy, kinetic energy, is changing between a maximum and zero. The total energy is remaining constant, but it is made up of different components of the energy. And there's a term here, thermal energy, which is always zero. And we will look at that in a little while. Now, before we go on to looking at damping in detail, what I'm going to ask you to do is to consider what the forces are, well, one particular force called the restoring force that is acting on this mass as it oscillates up and down. The restoring force is the total force acting on the mass that causes the acceleration. We already know that oscillations that undergo SHM have got an acceleration that's proportional to the displacement. I've now put in the masses at different locations within one cycle. And what I'd like you to do is to draw the direction and the magnitude of the restoring force, that's the force that causes the acceleration, in each of these positions. So you can just sketch it on a bit of paper. You don't need to draw the whole thing, but just call it mass number 1. What would the direction and the magnitude of the force be there? And so on for all of the others. And spend a couple of minutes doing that, and then once you finish that, we'll then go through the answers. So if you like, pause your video now and then come back when you're ready. Okay, so let's look at the restoring forces, and hopefully you've got something looking like this. The restoring force at the beginning for the first point when I release the mass is acting down towards the equilibrium position, has its maximum value because that's where the acceleration is a maximum. As the mass accelerates towards the equilibrium position, the acceleration decreases and the restoring force therefore decreases. Zero acceleration at the equilibrium point, and then as we go beyond the equilibrium point, the restoring force changes to a maximum and then decreases and then repeats as it was before. So this is what we call the restoring force. And in the animation that we were looking at just now, that restoring force is continually changing, but there's no damping. And what we mean by that, there's no external force that is causing a decrease in the amplitude. Right, so let's go back now to our animation, and we can see on our animation that if we increase damping, we haven't got a value associated with it, but we're just going to increase it to a small amount. Replay, but this time with damping. Let's see what happens. And pretty quickly you can see that the mass amplitude decreases, and not too long it comes to rest, or very close to rest. Over on the left hand side there's a key difference in that this time we've now got some thermal energy generated. So the total energy is still the same, but some of that energy that we started with has become thermal energy, and we're going to talk about what that thermal energy, where is it. So if we go back to our PowerPoint, this was our restoring force. If we now go on to the same diagram again as we had to begin with, now we've shown the mass in the different positions, but now under damping, you can see here that the mass doesn't reach the amplitude that it started with. So this time, what I'd like you to do is to draw on the masses the resistive force that caused the amplitude to die away. The damping effectively is caused by a resistive force that opposes the motion of the mass. So what I'd like to do this time is not the restoring force we looked at last time, but the resistive force. In which direction would a resistive force act on the mass in each of these locations? And again, I like to draw it to scale and get the direction right. Okay, like pause the video and then have a go at drawing that, and then we'll come back to it. Okay, so hopefully you've now had a go at drawing in the resistive force. Let's have a look at what they are. So, quite different to the one we had before. This time, when we release the mass, there's no resistive force at that moment. If it's due to air resistance that's causing the resistive force, because there's no motion, there won't be any air resistance. As the mass starts to speed up, as it increases its velocity towards the equilibrium position, the resistive force increases, and it reaches a maximum in the opposite direction to the way it's traveling at the equilibrium position. As it starts to decelerate and slow down, the resistive force decreases, and it's zero at the amplitude for the opposite direction. And then as the mass starts to move back up, the resistive force now again acts in the opposite direction, has its maximum value at the equilibrium position, and then zero here. So this is how the resistive force changes as the mass moves. And it's this force that's responsible for the damping and the reduction in the amplitude. Now, as that mass is moving, it's obviously pushing against the air. And since it's pushing the air, it must be doing work on the air, and the air is then gaining kinetic energy. So the surrounding air, which is providing the air resistance, is in turn gaining kinetic energy. And since the total energy of the system must remain constant, it means that the energy of the mass system must be reducing. Okay. Now I'm going to look now at different types of damping. So damping can be caused by air resistance, but it can also be caused in other ways. And within cars, for example, we have suspension systems which will remove the energy from the car. You wouldn't want the car to be bouncing around the whole time. And I'm going to show you now a simulation of this on a website called iwanttostudy.org, and it's got a large number of Java animations. So I need to just find that for you. Okay, so here we go. So we're going to start off with no damping, and just to describe what we've got here, the blue line here is representing the frame of the car. So this is the mass, effectively the whole car is modeled as this block here, and the tire of the car is at the bottom, and then you've got some spring suspension between them. So we're going to have a look at the system with no damping at all. We just imagine that we've maybe gone over a bump. What would we expect to see? On this side, we've got the graph. So let's have a look. So this should look fairly familiar. And what we've got here is an amplitude which is remaining constant all the time. So that means if you were in this car, the car would just be moving up and down continuously with the same amplitude, which would probably be quite uncomfortable. So what I'd like you to do now is, on your paper, is assuming that we start with the same amplitude this time, what we're going to do is we're going to introduce some what we call light damping. So the energy is going to be removed quite slowly with time. And I will add it on top of the graph that we've already got here. So what I'd like you to do is draw a sketch of how you think the light damping, the very light damping, might be different to the graph that's shown here. Okay, so if you pause your video now and sketch how you think the very light damping might compare to the one we've got here. Okay, so hopefully you've had a go at that. Let's have a look. So here goes the motion as before. It looks almost the same. What we can see is that straight away the amplitude is not the same after half a cycle or after one whole cycle, and the amplitude is decreasing as we go along. So there's a clear decrease in amplitude in each of the motions there. Now, how will things be different if we now increase the damping again? So we're going to just quickly look at increasing the damping a little bit more. So once the animation stopped here, we'll now move to light damping. We know the type of graph we're going to see. We're going to see a reduction in the amplitude, but see if you can spot another feature that's common to all of the graphs. Okay, so you can start to see that the increasing the damping is having a greater effect on the decrease of the amplitude. But the other thing you perhaps notice is that the period of the oscillation is remaining the same. So the point at which the maxima are reached is the same in each case. So although we're changing the damping, we're still maintaining the same period of oscillation as we had before. Now, the two other types we can look at as well, which we'll just quickly show here, which are important. One of them, which is really important in cars and vehicles, is called critical damping. We don't really want the oscillation to die away over time like this. We'd much prefer them to die away quickly, but then we don't want it to be too quickly that we don't get any decrease over time. We don't want a sort of sudden change because that'd be very uncomfortable. So critical damping is this one. Critical damping is the damping which causes the system to return to the equilibrium point in the shortest possible time. So if you were in a car, the car suspension is designed to have critical damping. It doesn't want to oscillate over and over. There is one more type of damping which I'll refer to called heavy damping. And heavy damping is such a large amount of damping that the graph, the amplitude decreases very, very slowly. So it takes a very, very long time to get to the equilibrium position, and that wouldn't be really suitable. If you were still, if you go over a bump and it's still taking several minutes to get to the equilibrium position, that wouldn't be suitable either. So critical damping is the one that we would refer to most in most situations. Okay, now in the laboratory, we are able to generate damping quite easily. We would expect to have it anyway, because even a mass on a spring is going to experience air resistance. But if the mass is quite heavy and is oscillating with a small amount of area that's opposing the air, then the air resistance will take a very long time to bring the oscillation to zero. So for that matter, what we can do is to introduce something with a large surface area. So this piece of card attached to the masses on a spring gives us a large amount of air resistance for the same mass. And in order to obtain some data for this, what we could do is video it, or an alternative would be to place a motion sensor that uses ultrasonic waves, so ultrasound, the ultrasound directed up and then reflected back down off the card, and the time of the interval then returns to a data logger and converts to a displacement. So an ultrasonic data logger would enable us to monitor the position of this card over time. And we've done this in the lab at BASVIC. We would normally show this to you in the lab, but obviously we can't do that just at the moment. So okay, so I think I'm on the wrong slide. I should be on here. So here we have the data that was obtained from releasing the mass with the card on it, and each blue dot is an individual data point. So as the card is released, it moves up and down, and we get this trace. So you can see the time between the maximum seems to be, by eye, about the same each time, even though we're obviously decreasing. We have some damping going on. You can see that that's decreasing. Now, the heading for this is exponential decay, and that's because this curve that was sort of mapped out by the changing amplitudes follows a very mathematical curve called exponential decay. And at this stage, we haven't done a lot of exponential work. It becomes more common in A2 when we look at things like capacitor decay and radioactivity. But although we don't need to do the maths of exponential decay for damp systems, it is actually quite an interesting one to look at, because it's quite easy to see from the data that there is this exponential decay going on. So what I'd like to try and do is to follow the instructions here. It says, is this an exponential decay? Well, if it is, it should exhibit something called half-life. You'd be familiar with half-life from radioactivity. Now, half-life is the time it takes for the initial value, in this case the amplitude, to halve. So in fact, the initial value was down here. So 0.06, 0.07, 0.08, 0.09 was the value of the amplitude at the beginning at t equals 0. What we'd like to do then is to use this trace to see if you can work out what the half-life is in time. So how long does it take for this value to halve? And then maybe take the next point and work out how long did it take for that point, that amplitude, to halve, and then repeat it for maybe 5 or 6 other points. Do you always get the same half-life, or is it changing? A feature of exponential decay is that the half-life should remain constant. So what we're asking you to do is to verify whether this actually is exponential decay by finding out the half-life. Okay, for this particular activity, you don't need to use natural logs or anything, but in the second year, we will be moving on to equations of this form. A equals A naught e to the minus kt, A being the amplitude at time t, given that you started with amplitude 0 at t equals 0. So obviously not all of you are used to seeing exponential decay, but this is just the form of the equation that will be coming up. So just for now, if you could look at the half-life and see if you can work out whether the half-life is constant. Pause the video, and when you've done that, we'll carry on. Okay, so I'm hoping that you saw that it was close to being exponential. To go down to 0.45 was around about somewhere between 10 and 12 seconds. And that repeats over and over. So this is a good example. This is real data, and we actually get some changes where it appears to increase. Now, there is a reason for that, because the oscillations of the mass on the spring actually sometimes have other modes. In other words, it wasn't just going up and down, it sometimes starts to go side to side if there's an air current, and that's what causes that data to change in a way that you wouldn't expect. But in general, it's doing what we would expect. Okay, now the next stage we're going to look at is damping with resonance. Now, so far, the damping that I've shown you has been to do with free oscillations. So just releasing something and allowing it to come to rest. What happens though if we are driving the oscillations? And so, as from your previous lesson, you've looked at resonance. What happens when we have resonance going on? How can we use damping in that case? So to do this, I'm going to take you to a series of animations at Salford University. I should say Salford Acoustics. It's just overlaid by the graphic. But you can get the link to this again after the video. So let's look at Salford Acoustics, and hopefully got that on here. Okay, so this is quite a nice way of explaining it. So we've got a truck. Now imagine that we have a truck on a rather bumpy surface. The bumps, if you like, are causing a driving frequency. If you're going at one particular speed, you might be hitting bumps at a certain rate, and that would then be causing the truck to oscillate like this. So here we've got the bumps. I mean, it's a bit artificial, but we're imagining the bumps are at regular intervals, and that's driving the oscillator of the car. We could imagine that the car is just modelled as a mass on a spring, much like we've done before. So as this car is moving along at a certain speed, we are driving the car. Now the car has its own natural frequency, but the frequency of the bumps might be different because of the speed we're driving at. As you know, if the driving frequency matches the natural frequency of the car, we get resonance, and we get very large amplitude oscillations occurring in the car. So it would be very important for us to remove the energy of the car so that we don't get a catastrophic situation where the car might bounce off the road, or parts of the car might come apart, something like that. Or if you were carrying a heavy load, you might shake it about and destroy it. So we need to think of a way of overcoming this. So in order to avoid getting resonance, we can't avoid really traveling at 50 miles an hour. If we do want to avoid the resonance, what we would do is use some form of damping system. And here we've got an example of the means by which we can produce damping. So we have a piston filled with fluid, And as the piston is connected, the piston head is connected to the car, as it moves up and down, it pulls the piston through a liquid, which forces the liquid to move up and down through small valves. And that in turn causes energy from the vehicle to be transferred to the liquid. So the liquid will get warm in this process. But the liquid provides the resistive force. And remember, we were looking at the resistive force much earlier when we were looking at the direction of the arrows. So this is a good example of how you can produce damping in a real mechanical system. And this is quite a simplified model of it, the diagram here. They are sometimes much more sophisticated than that, but this is just one way that you can produce the damping. Now, we've now looked at light damping, heavy damping, critical damping, and so on. How do the different forms of damping affect the resonance curve? This is what you have been looking at in your previous lesson. You know that resonance produces this peak, which we're trying to avoid. So if we can introduce some form of damping, we can reduce this peak down. So with very little damping, we get quite a high peak. But as that damping increases, we get a whole family of curves. And what happens is that the peak of that curve follows a slightly curved line. You can see here that the blue line peaks slightly over to the left of the natural frequency of the system. So this is important that you appreciate that as the damping increases, the peak of the resonance occurs to the left of the natural frequency, and it occurs at a lower amplitude. As an example, there's always a film that sticks in my mind, which I think would be well worth watching to show the importance of shock absorbers, is a film made in 1953 called The Wages of Fear. And it basically shows how a highly explosive liquid called nitroglycerine was transported across very rough terrain. And the problem with nitroglycerine is that it can detonate by shaking it. So if you were a lorry driver taking nitroglycerine from one place to another, you'd want to make sure that the suspension of your vehicle was absolutely perfect. In this film, which I won't spoil it for you, but it is an amazing film, it shows some of the problems of trying to transport this material when you have a vehicle which hasn't got perfect suspension, and how the people overcame it. So if you're interested, it's a film with subtitles, but it's really, really good. So there you go. The Wages of Fear. Now, to finish off with, what I'd like you to do is some research. So there are a number of examples, many examples, where damping is used to reduce the amplitude of an oscillating system. I've put a few here, but actually it's up to you. I'd like you to choose two. The i360 tower in Brighton is capable of oscillating up to 1 meter at the top. It's safe to do so, although it wouldn't be very comfortable if that was going on. But it incorporates some internal features designed to remove energy from the tower if it were to oscillate. So can you find out some information to explain what the i360 tower does in order to remove that energy? Mountain bikes, the one I have, doesn't have any suspension. It was such an old bike. But modern mountain bikes, trail bikes, have often front suspension and rear suspension. And the idea would be then to explain what is the suspension that's used to achieve a reduction in vibration of the bike. Musical instruments, damping can be used in lots of different musical instruments. So if you are a musician, can you come across some examples of damping used in the instrument itself, or methods to play it which incorporate damping? The Millennium Bridge in London, when it opened, exhibited a wobble when people started to walk over it. Very soon became a bit unnerving for the designers, and so it was closed very quickly while it was analysed and measures put in place to stop it from wobbling in the future. What was done there? There's plenty of information about what was done. How did they stop the bridge from wobbling? The Burj Khalifa is an immensely tall building. It has a very interesting damping system at the top of the building. Can you find out how the Burj Khalifa is maintained in without having large swaying at the top? So how does the damping work there? Alternatively, if you've come across anything else, and one that springs to mind would be earthquake design of buildings, but any other example of damping that you're interested in, or you come across, that would be acceptable as well. So we're looking for one paragraph which just highlight, or maybe a sketch of a diagram, and what we'd like you to do is to have it ready for the last lesson of the week, so that you can maybe just share it with the rest of your class as to what you found. Okay, thank you very much.